Welcome into today's daily question. Feel free to pause the video and give this question a try. I'm going to go ahead and go through the solution now. So what is the electron configuration for Cu+, so the copper +1 ion? So copper, Cu is right here on the periodic table. So if we just started by writing out the full electron configuration for regular copper, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d9. At least this is what we would kind of expect based on the periodic table, because this is the 3d section right here. Okay, this region is the D block. And then we're in the 1, 2, 3, 4th row. But for the 4th row, or excuse me, for the D block, you do the row number -1. So the D block in the 4th row is actually 3D. The D block in the 5th row would be 4D. So this is what we would sort of expect. However, copper, just regular copper, is already an exception. So first we need to consider that. The reason it's an exception is that the D sublevel can hold up to 10 electrons, meaning that it has 5 orbitals. Okay, so if we just focused on the 4s and the 3d, 4s and the 3d, for copper, we would expect its orbital diagram to look like this. However, it is just one electron away from having a full 3D sublevel, from all 5 of its 3D orbitals being full. And that provides a stabilizing effect. So what copper actually does is it is actually going to move one of these 4s electrons into the 3D to fill the 3D sublevel. Even though 3D is higher in energy than 4s, this filling of the 3D sublevel more than offsets that. So the regular electron configuration for copper would actually end with 4s1 and 3d10. It's an exception. Or if we wrote this in the noble gas form, that would be Ar 4s1, 3d10. That's for regular neutral copper. So Cu plus, it has a +1 charge. That means it lost 1 electron. So we have to take away 1 electron. And then where are we going to take it away from? Well, you might think 3D, since that's at the end of the electron configuration. And the reason it's at the end is because it's the highest amount of energy. Okay. And you just naturally, if you just go in order of the periodic table, so hopefully you know that this is the 4s right here. Okay, because these 2 columns are s, these 6 are p. I already mentioned 3 through 12 is d, and then, if we're in the first row, it's 1s, second row, it's 2s or 2p. It's just with d, you do -1. So if we're in the 4th row, this is 4s. Okay, but then for D, we do -1. So this is actually 3D, not 4D. And then once we get to P, Well, we don't for copper, but if you did, this would go back to being 4p. So if you just go in order of the periodic table, you're naturally going from lowest energy to highest energy. So since 4s comes before 3d, 4s is lower in energy. However, and because it's lower in energy, it fills first. Okay, so 4s fills before 3d. Now there was this exception with copper, but typically 4s fills before 3d. However, when we're removing, we also will always remove 4s before 3d. And the reason is because when we're removing, we're not focused on the actual amount of energy, but we're focused on like the valence electrons, which is purely based on this front number. Okay. These are in the fourth energy level. Think of like the Bohr model. Okay. And these are in the third energy level. Okay. So these ones in the 4s, they're farther away from the nucleus. Those, or I guess there's only one in this case, is the valence electron. It's in the outermost shell. And so that one's going to be removed before the 3D. So we're removing one electron. It is the one in the 4s. So our electron configuration of Cu plus would be, and then if we do that again down here in the noble gas version, it would be argon 3d10.